All right, so what we're going to do in chapter 6 is talk about something called eigenvalues and eigenvectors and this notion of diagonalization. Um, so the use of eigenvalues is amazingly broad. I mean, you'll use them in differential equations a lot. You'll use them in physics a great deal and whatnot. And also they play a role in even discrete math when you use matrices like in graph theory and whatnot. So they're definitely important. So what we want to first focus on, of course, is defining what they are and learning a technique to actually find them. All right, so let's just start off. Um, so let's just going to leap in here. I'm going to compute. I have a matrix, and I have two different vectors, and I'm going to compute AU1 and AU2 just to kind of see what all happens here. So if I compute AU1, we know that the product is defined. Inner dimensions are the same. Right? So what you expect to happen here is to get a 2 by 1, right? Because this is 2 by 2, this is 2 by 1. Inner dimensions are the same, and the outer dimensions specify the dimensions of the output. And so you expect to get 2 by 1. And what you get, if you take row dot column, you get minus 2 plus 4 is 2. 1 times 1 plus 1 times 1 is 2. But notice that I can yank a 2 out easily to get 2 times the vector 1, 1, which remember what u1 was, that was 1, 1. And so I've managed to rewrite, or managed to compute a matrix times u1, and I got a scalar multiple of the vector u1 itself. All right, let's do the same thing for AU2. So AU2, you multiply this matrix times u2. Okay. Same idea, row by column, and this time minus 2 times negative 4 is 8, plus 4 is 12. Negative 4 plus 1 is negative 3. And I'll yank out a negative 3 to get negative 3 times negative 4, 1. And again, notice here, u2 was the negative 4, 1. And so I've managed to compute this guy, and I got another scalar multiple of itself. So when that happens, right, whenever you can transform a vector u1 by multiplying it on the left by a matrix, and the result gives you a scalar multiple of the original vector, that's of importance in applications. And what we're going to do then is call the u1 and the u2 eigenvectors of A, right? A vector u is an eigenvector of A if you can find some scalar so that when you multiply u by it, you get the same thing as what you got by multiplying u by it. Okay? And so this happens. You can find some lambda. So here, this 2 was the scalar that made this work. That 2 is called an eigenvalue corresponding to this eigenvector. And same way here, this scalar happened to work. So that is the eigenvalue corresponding to that eigenvector. Okay, 2 new words to add to your list of vocabulary there. Okay, if you look at a linear mapping, right? So remember, we always have this connection since we have linear mappings being defined as matrices times a vector, right? There's this obvious connection between talking about AX and talking about T of X for that particular matrix A. And so notice that if I compute T of an eigenvector, right? So suppose I'm up here and the mapping is T of X equal to AX, where this is my A. Well, if I compute T of U1, by definition, that's just A times U1. But what we found was that that was equal to 2U1. All right. And so what this tells you is that if the input of your linear transformation is an eigenvector, the output is a scalar multiple of that eigenvector. So a linear transformation takes a eigenvector to a multiple of itself. Okay, so that's how it acts in essence. All right, so let's look at this. So back here rather. So another way to write that, that's the definition, but a more mechanical way to write it is that if I take the lambda u to the left, so I subtract lambda u from the left from both sides, I get that guy. And by our distributive property, right, I can rewrite this in this way. So you have to be careful here. Just don't write a minus lambda. Lambda's a number. So a is a matrix, lambda's a number. If I just wrote that, that would be meaningless, right? So you're really multiplying lambda times the identity matrix. So this guy times u is equal to the 0 vector. All right, and so this is an alternative definition. Right, and here I'm using the I sub n. If A is an n by n matrix, I have to have the dimensions be the same. So this is the identity matrix that is an n by n form. So 1's on the diagonal, 0 everywhere else, n by n. Right, so these mean the same thing. Right, and the reason I write it like this is we're gonna look at this in particular to find eigenvalues shortly. All right, let me scoot this up and, all right. So the next thing we want to do is determine if each of these vectors is an eigenvector of this matrix A. All right, so if this is going to be an eigenvector of A, then when I multiply on the left by A, the output should be a scalar multiple of that vector. That's what it means to be an eigenvector. All right, so let's see. I'm using the same A from example 1. So I have minus 2, 4, 1, 1 times 3, 1. If I do that multiplication, row by column, negative 6 plus 4 is 2, 3 plus 1 is 4. I can pull a 2 out, but that's 2 times the vector 1, 2. That is not a scalar multiple. Oh, that should be a negative 2. In either case, it's not a scalar multiple of that guy. And so not of the form. Remember, in order for this to be an eigenvector, the output of multiplying on the left by A should be this times a scalar. So it should be lambda times 3, 1, and that is not what's happening here. So this is not an eigenvector of u. If I do this one, look at A3, 3. If I multiply minus 2, 4, 1, 1 times 3, 3, minus 6 plus 12 is 6. 3 times 1 plus 3 times 1 is another 6. And I can write this as 2. I can pull a 2 out times 3, 3. And so that is an eigenvector. A times this vector is that vector times a scalar. So this is yes. Okay. And same way here, if I multiply A times that guy, right, what I get row by column, I get minus 24, 6. And I can rewrite that as minus 3 times 8 minus 2. I can pull a minus 3 out. Okay. So notice again, A times that matrix is a scalar times, I'm sorry, A times that vector is equal to a scalar times that vector. And so that's a yes. All right. Now, also make a note here that these two guys up here, those two, we showed were eigenvectors of A. This guy and that guy are scalar multiples of those eigenvectors, right? So what that suggests might be happening is that if I already have two eigenvectors or an eigenvector in hand, maybe I can produce other eigenvectors just by multiplying it by a scalar. All right, and so that's what the claim is here. Let's actually see if that's true. So let's let C be a scalar, right? C is a non-zero scalar. And I'm going to multiply that by an eigenvector, right? So I'm going to assume that U is an eigenvector for A. And my question is, if U is an eigenvector of A, must CU be an eigenvector of A? Well, if it is, I have to be able to rewrite this as some lambda times CU. All right. Well, all we know from knowing that U is an eigenvector of A is that AU is equal to for some lambda. Right, so AU can be expressed as lambda U for some lambda. Well, but this little c's in the way. But remember, we have that sliding scalar property for matrix multiplication that we introduced back in 3.2. And so I can pull the c out like that. And now I just have the lambda u where I know what that equals. That equals that lambda u. Okay. But remember, I want to write that as lambda times cu. But we can do that. Remember, here, multiplication by two scalars, you can interchange the order of those scalars because they're real, and multiplication in the real line is commutative. And so I can rewrite this as lambda times cu. And so the minute u is an eigenvector, any non-zero scalar multiple of it is also an eigenvector of A. Okay, so that is a true statement. All right, so let's go on to example 3. If I can get this position right. All right. All right, sorry. All right, so I have a matrix A, and I have two eigenvalues, 5 and 1. So I have the lambdas, and what I want to do is find the vectors u that work. All right, and so here, from the first one, I want to find a vector u1 such that if I multiply that vector on the left by A, I get 5 times that vector. Right, so this time I'm trying to find the actual eigenvector. I'm not giving you one and asking you if it is one. I'm saying I have the eigenvalue. Right, now can I use that to find the eigenvector? And so here I want to find u. I'm going to take everything to the left side. Like I said, up above. I'm going to pull out the u1. So I'm going to rewrite this as A minus 5 identity in 2 space, or 2 dimensions rather, equals 0. But notice this is a matrix. I have a matrix times a vector equal to 0. That's a homogeneous system, right? So here, all I'm doing, I'm going to compute this in. So A minus lambda, or 5 times I2. Let's actually compute that. Here's 4, 3, 1, 2 minus 5 times the identity, right? But remember, I can pull in that 5 on all the entries, but the only ones it's going to change are the diagonal because you're multiplying the other guys by 0. And so to subtract those, I subtract coordinate or component wise. But again, the only difference is going to occur on the diagonal. Okay, and then so that's equal to -1, 0, 1, -3. All right, so the easy shortcut here, you don't have to compute through all that nonsense every time. Just realize then when I'm computing that, the result is just the matrix obtained by subtracting the eigenvalue from the diagonal of the matrix. That's all we ended up doing here, right? And so A minus 5I2 is -1, 0, 1, -3 times U1 equal to 0. And now I would just want to solve this, right? So why don't I want to put this into echelon form. So why don't I just add R1 and R2. And put that into R2. So I have -1, 0, 0, and -3, right? And this is times U1. All right, and so in this case, did I subtract? I think I might have subtracted something wrong. Oh, I forgot the 3 here. I was going to say this doesn't actually seem to work. All right, sorry about that. So there should be a 3 here. And if I added those guys together, I get a 0 there too. Sorry about that. All right, so notice I have a row of zeros. And so what that tells you is that this guy is the pivot, that guy is free. So I'm going to let x2 be s. x1, therefore, remember from here, it's negative x1 plus 3x2 equals 0, right? Because I'm setting this whole thing equal to the 0 vector. X2 is equal to 1/3 x1. Oh, the other way around. Sorry, x1 is equal to 3x2. You can do it either way. And so x2 was s. All right, and so the eigenvectors, so the u1s that work are 3s, s, where s is in R, and I can pull out the s. Right, so that set are all of the eigenvectors that correspond to that eigenvalue. It makes sense that we're getting a scalar multiple times these guys because we just said a scalar multiple of an eigenvector is an eigenvector, right? And so if you were just to get a unique solution here, that would contradict that. And so the fact that we got 3,1 is our kind of basic eigenvector, and we can multiply it by any scalar you want to get them all, right? So this is the eigenspace of A corresponding to lambda equal to 5. So eigenspace is simply a collection of all the eigenvectors that corresponds to lambda equal to 5. Okay. Notice that it's also equal to, remember the way we got this was by solving that homogeneous system. And so we know the solutions of that are the null space of that matrix, right? So the null space of A minus 5 lambda 2 is the eigenspace for lambda. They mean exactly the same thing. Hold on, let me let my dog out here. Go on. Okay. All right, so that was a mouthful. Let's actually do the other one. All right, so same matrix. Let me just copy it down here. We'll go through the same exact thing again. So we have A equals 4, 3, 1, 2, and we have an eigenvector lambda 2 equals 1. And what I want to do is find the eigenspace. I want to find all the eigenvectors for A that corresponds to lambda 2 equal to 1. And so we want to find all vectors, and I'm going to call them U2 because they're going to correspond to that eigenvalue, such that AU2 is equal to lambda 2 times U2, and that lambda 2 is just 1. Okay. So the first thing I do is I pull the U2 to the left. Okay. And I'm going to yank the U2 out of both, but in so doing, remember what I have to do. I multiply the eigenvalue that's there times the appropriate identity matrix. Right, so again, A minus 1 doesn't make sense. A minus 1 times I2 makes sense. That is a matrix. All right, and so this one, you just subtract the number 1 from all diagonal entries of A. Right, and so what this matrix turns out to be is 3, 3, 1, 1. And that's times U2 equals 0. All right, so I'm finding all the vectors U2 such that this happens, right? So you're finding the solutions of this homogeneous system. That means that the solutions U2 are in the null space of that matrix, just by definition. Go back to the definition of what a null space is, and you'll find that that's true, right? So I'm just applying that definition now to a matrix of that form. Okay, And so this is easy enough. All I have to do, let's actually interchange these two rows, right? So this matrix is, this system is the same as this one, right? So R1 is being swapped with R2, and it's clear what's going to happen. I'm going to multiply R1 by -3, add it to R2 and put it into R2, right? And so I'm going to get 1, 1, 0, 0. U2 is equal to the 0 vector. Okay. And so here is your pivot, here is your free variable. So I'm going to again let x2 be s. Then x, remember here from that equation, x1 plus x2 is equal to 0, right? And so x1 is negative x2, which is negative s. Okay, so what we conclude, these unknowns, remember I called this unknown x1, x2. That's where these x1s and x2s are coming from behind the scenes, right? Those are the components of our unknown vector u2. So u2, well, those are these vectors. If you plug them in, you get negative s, s, and I'm going to pull out the s. And s could be any real number it wants to be. Right, so all of these guys are solutions to this system, and that system arose from the definition of what it meant to be an eigenvector corresponding to lambda equal to 1. And so the eigenspace of A corresponding to lambda 2 equal to 1 sorry about that. Wrong way. Here we go. All right, is the collection. So that's all those guys. So you multiply -1, 1 times any scalar you want. Right, so that is what the eigenspace corresponding to that lambda is. And we also call this, just using our old terminology, we also call this the null space of the matrix that I used to get my homogeneous system, which is just 1. Right, so let me write that over. It's A minus the eigenvalue, which was 1, times that appropriate identity matrix. All right. So that is a clean example of going from a matrix with an eigenvalue to finding the eigenspace. One further thing we can say, notice that the eigenspace is just the scalar multiples of that particular vector. And so technically we can say that this is the span of the set containing just that single vector. And a vector is certainly linear independent to itself. And so a basis for the eigenspace corresponding to lambda 2 equal to 1 is just that single vector. Right, it's just that vector itself. Remember, a basis is the vectors, the specific vectors you need, so that when you take the span of those vectors, you generate the space of which it's a basis. And so here, the space of which it's a basis is the eigenspace of A, right? This, by definition, is just the span of that matrix, or that vector. And so that vector itself is a basis for the eigenspace. Bunch of definitions all coming together at one time. Okay, so we'll see more examples of this shortly. All right, so in our workings so far, we came up with writing that guy out, right? And so we use that system to find the eigenvectors. So now notice though, that only had a solution when, or it non-trivial solutions when U was not invertible. If u is invertible, I can multiply both sides by the inverse of that matrix. I'm sorry, when this, not u is invertible, when this guy's invertible. If that's invertible, I can multiply both sides by its inverse on the left. If I multiply any matrix times the zero vector, I get the zero vector back, right? And so if that happens to be invertible, then you only get the trivial solution. So the interesting thing is when it's not invertible, right? If it's not invertible, its determinant is zero. Remember, that was that equivalence that we had back with invertibility. A matrix B is invertible if and only if its determinant is zero. So the only interesting case that we're going to get was when this guy is equal to zero. All right. And so we call that the characteristic equation, right? Just a new term that we give to that because it's important. It characterizes what the eigenvalues are. And notice the only unknown here is the lambda, right? And so what we can do is if I give you a matrix and I tell you nothing about the eigenvalues or the eigenvectors, what you'll want to do is actually find the eigenvalues and then find the eigenvectors. The way you find the eigenvalues is by taking the determinant of a minus lambda I n, where lambda is what you're trying to find, setting that equal to zero and solving for lambda. Right, so this is how you find the eigenvalues. All right, so let's actually do that. Let's find the eigenvalues and eigenvectors for just this 2 by 2. All right, so the first thing you want to do is you want the determinant of a minus lambda I2. Remember I2 because this is a 2 by 2. And that just means subtract the lambda from the diagonal of A and take its determinant. Right? That's how we saw before. If you actually wrote it out, this would just be the matrix lambda 0, 0, lambda. When you subtract component-wise, the only non-zero entry that you're subtracting occurs on the diagonal itself. All right, and so this is the determinant of the matrix 2 minus lambda, 5, 4, 3 minus lambda. Okay, and you want to find lambda such that that's equal to 0. All right, well, we know how to compute a 2 by 2 determinant. Multiply down that way, subtract, multiply up that way. And so you have 2 minus lambda times 3 minus lambda minus 20 equal to 0. And then to solve that, I'm going to multiply that guy out, right? And so this is the same thing as lambda squared minus 5 lambda plus 6 minus 20 equal to 0. Just FOIL it out, and I'm changing the order as I do that. And I can add those as negative 14. This time it factors. They don't always, but this time it factors as lambda minus 7 times lambda plus 2, right? And so the eigenvalues are 7 and negative 2. Okay. Now, all you have to do to find the eigenvectors, you do it one by one. Right? So if lambda is minus 2, the eigenvector or the eigenvectors are the solutions to equals minus 2u. So the u is what you're trying to find here. Okay? And so remember, this is equivalent to I take everything to the left, a plus 2i2 times the vector u equal to 0. And so let's add the 2 to the diagonal of A. So I get 4, 5, 4, 5 times u equal to 0. If you subtract the rows and plunk it into row 2, you get this matrix times u. Obviously, that's the pivot, and this is the free variable. So let x2 be s. All right. And then x1, well, 4x1 plus 5x2 is equal to 0. Put an s in here. That's 5s. Subtract from both sides and divide by 4. Negative 5/4 s. And so the eigenvectors, I can take, I have a 1 here, or no, a negative 5/4 there and a 1. So x1, x2, and I'm going to pull the s out. And so here we have all the eigenvectors, but I'm just going to use that guy, right? So we'll call that the basic eigenvector corresponding to that particular lambda value. All right, let's roll this up a bit. Okay, and so I have the eigenvector for lambda equal -2 is -5/4 1. The eigenspace, I want to get you used to all these definitions, corresponding to this guy is the collection of all of them. So it's the span of that vector. This is the basis for the eigenspace. All right. Do exactly the same thing for lambda equals 7. So I have lambda equals 7. Let me put the a down. This is just continuing that same problem. Give you that guy. And so you want to find u such that au is equal to 7u. Take the 7u to the left, right? And this is equivalent. I2 u equal to 0. Subtract the 7 off the diagonal of a. So I have -5, 5, -3, 3 times u equal to 0. If I just add them again, or no, not just add them. Certainly if I multiply row 1 by 3/5, right, and negative 3/5, and add that to R2 and plug it into R2, I'll get this. All right, so it's a little bit of manipulation there. Same idea. We have a pivot and a free variable. Let's let x2 be the s. And then x1, we have -5x1 plus 5x2 is equal to 0. The 5's go. And so x2 is equal to x1. Just take that to the right. Okay. And so we know that our vector u is equal to 1, 1 times s, where s is any real number you want. Right. And so we'll think of this as the basic eigenvector corresponding to lambda equal to 7, but the eigenspace corresponding to lambda equals 7 is all of these guys. It's the collection of all of those vectors. That's just the span of the vector 1, 1. Okay. All right. So that is for 2 by 2. We've gone through that process a couple times. Hopefully it's starting to congeal. It's going to take a little while. But okay, so if you go to example 5 on the page, example 5 is another 2 by 2. Do that one on your own. All right, so that one is very much a rehash of what we just did. I want to get to a 3 by 3 of interest. And so I'm going to get down, I'm going to actually go to C. All right, so I just want to do one of these because they take a while. And this one will be, it'll be a 3 by 3, so you can actually see how the determinant of that a minus lambda I for a 3 by 3 goes. So we'll find the eigenvalues, and then the eigenvectors are going to be a slightly different beast this time because of the nature of the eigenvalues. So there's something I want to illustrate there. Okay, so I'm just going to go to a new page. I'm going to write this matrix down just so I don't have to keep changing pages. All right, so my A for part C is 1, 2, -2, -2, 5, -2, -6, 6, -3. All right, there is my matrix. And I want to first find the eigenvalues. right? And so the eigenvalues are obtained by solving the determinant of a minus lambda I3 equals 0, right? And remember, that just means for a minus lambda I3, I'm just taking the lambda and subtracting it from the diagonal. So I have 1 minus lambda, 2 minus 2, minus 2, 5 minus lambda, minus 2, minus 6, 6, minus 3 minus lambda. I want to compute the determinant of that matrix and set it equal to 0 and solve for lambda. Okay. Well, one thing you can do, well, let's actually just, I'm just gonna, there's no nice way of doing this. I'm just gonna use the top row and break it down into cofactors. All right, so I have 1 minus lambda times the determinant of what remains if I throw out the row and column containing it. So it's of this guy. 5 minus lambda minus 2, 6 minus 3 minus lambda. Okay. Plus, and there's a negative 1 squared out in front there. Negative 1 cubed times 2 times the determinant of what remains if I throw out those guys, which is minus 2, minus 2, minus 6, minus 3 minus lambda. And then plus negative 1 to the 4th times negative 2 times the determinant of what remains if I throw those guys out, minus 2, 5 minus lambda, minus 6, and 6. Okay, and that's to equal 0 in the end. All right, well, let's multiply this out. Negative 1 squared, negative 1 to the 4th are just positive 1s. This is just a negative 1. I'm going to compute each of these determinants. So I have 5 minus lambda, minus 3 minus lambda, minus a negative 12 is plus 12. And then minus 2 times 6 plus 2 lambda minus 12. And then a minus 2 again times negative 12. And then minus that product is plus 6 times it. So plus 30 minus 6 lambda. And that's to equal 0. So just simplifying. All right, now multiply these things together. I'm going to distribute this guy through. Okay. So I'm going to distribute that guy through. So I have 1 minus lambda times 5 minus lambda minus 3 minus lambda plus, I'm going to multiply that out. And so I have a 12 minus 12 lambda. So plus 12 minus 12 lambda. Here I have, let's see, actually, what it would have been, okay, so this here is minus 6 plus 2 lambda, right? And so what I'll do is I want to get these in both. So I'm going to pull out a, let's see, is that plus 2 lambda? Hold on one second. Minus 2. Oh, that, yeah, I'm good. I'm going to pull out a, just making sure here. Yeah. All right, I'll just multiply it through. Plus 12 minus 4 lambda. And then I'll multiply that through and see what happens. So what I don't want to do is multiply this out, right? Because then I have a lambda cubed. I want to see if I can factor something out. I'm going to distribute those guys, though. This is negative 18, positive 18. And so I have a minus 36 plus 12 lambda. All right, so I just grouped those together as positive 18, multiplied by this minus 2 to get that guy, and then I multiplied those guys. All right, so thankfully, notice this went, right? I have 12 plus 12 is 24 minus 36. Minus 36, 24 minus 36 is negative 12 minus 4 lambda. But notice here that rather than multiplying this out, I'm going to rewrite I'm going to pull a -4 out of there, or +4 rather, times a -3 minus lambda, right? So if I pulled a 4 out, that gives me -12 minus 4 lambda. But the reason I did that is so that I can yank that guy out. Okay, and so let's do that. -3 minus lambda comes out. And then what I'm left over with inside is that. But I still need to simplify this inside. That's just quadratic. So it's a little bit easier to do that. It'll yield a polynomial that's easily factored. If I FOIL this out, I get lambda squared minus 6 lambda plus 5, and I have that plus 4 there. So this is equal to -3 minus lambda. This is lambda squared minus 6 lambda plus 9, but that is a perfect square. It's lambda minus 3 squared. Finally. So the determinant of a minus lambda I3 equal to 0 is equal to this equation, right? So I don't need these equals here. Each of those should have been equal to 0. Okay, so I should have put equal to 0 along the way. Okay, and so now you have a product of factors involving lambda. You'll get lambda equals 3 and -3, but lambda occurs twice. It's repeated. It's a repeated eigenvalue. And so it's that one that's going to cause a slight change to the nature of the eigenspaces. All right, but anyway, we have the eigenvalues. Now let's go through and find the corresponding eigenvectors. All right, so let's do the non-repeated one first, namely lambda equals -3. And so I want to find u such that a times u is equal to -3 times u, right? So this would be the eigenvectors corresponding to that guy. So let's pull it over. We have our A matrix, right? So this is equivalent to A plus 3I3 times u equal to 0, right? So that means the same thing. And so I'm going to add 3 to the diagonal entries of A to get the matrix I'm interested in. And so if I do that, I get the matrix 4, 2, -2, -2, 8, -2, -6, 6, 0. Okay, and that's times u equal to 0. And again, I'm letting u behind the scenes being this unknown vector with those components. Okay, well, to solve that, we have no choice but to put it into echelon form, right? And so I want zeros in both of these positions. Why don't I, first thing I'm going to kill a 2 throughout, I think. Or no, let's see here. Yeah, I'm just trying to get nicer things. So I'm going to interchange rows 1 and 2 first. You can piddle around with this any way you want, but I'm just trying to ease the arithmetic. Right, so I interchanged rows 1 and 2. And then I'm also going to kill factors of 2 and here 6 if I can. So I'm going to multiply row 1 by a -1/2 and replace row 1 by it. I'm going to multiply this guy by 1/2, replace row 2 by it. I'm going to multiply this guy by 1/6 and replace row 3 by it. Right, so doing that, I'm not going to write all that out, but doing those 3 things, I get 1, -4, 1, 2, 1, -1, -1, 1, 0, right? That matrix is easier to deal with in terms of arithmetic. Okay, so now to put it into echelon form, I'm going to multiply row 1 by -2, add it to row 2, put that into row 2, and I'm going to add row 1 and row 3 and put that into row 3. All right, and so what I get, if I do that for these guys, I get 0, So multiplying row 1 by -2 and adding it to row 3, 9 and -3. And then if I just add rows 1 and 3, I get 0, -3, 1. All right. Well, now I want a 0 here. And so I'm going to multiply row 2 by 1/3, add it to row 3, and replace row 3 by it. And so I get this guy, this stays as it is. And then if I do that, 1/3 of that plus row 3, I get a row of zeros. Okay. And let me just multiply 3 here by 1/3. All right, so just again to simplify matters going forward. So I just multiplied row 2 by 1/3. Okay. And so I have that matrix in the end. The pivots, remember you're trying to solve that system, don't lose track of what you're trying to do. So I put it into echelon form. Now I'm going to go back to the system form. Those are the pivots. I only have the one free variable, namely this guy. All right, so that is free. And so let's let x3 be s. Then from that equation here, we know 3x2 minus x3 is 0. So add x3 and divide by 3. x2 is 1/3 x3, so 1/3 s. And then x1 minus 4x2 plus x3 is equal to 0. Put in s for that guy and 1/3 s for that guy. So I have x1 minus 4/3 s plus s equal to 0. x1, that's minus 1/3 s. And so x1 is also 1/3 s. Okay. So the eigenspace for lambda equal -3, remember the vector, so the solutions, remember the u's I was looking for are of that form. Go back to the components. I'm going to plug in x1, x2, and x3, but I'm going to yank out the s. Okay. And so for any s and r, that would be an eigenvector corresponding to lambda equal -3. And so the eigenspace corresponding to lambda equals -3 is the span of just this vector. Okay. And so this gives you a basis for the eigenspace. It is the single vector in this case for which the span is the eigenspace. So it's just the single vector. All right, and that has a dimension of 1. So the dimension of the eigenspace corresponding to lambda equals -3 is 1. Remember, it's the number of vectors in the basis. Okay, so that actually, though the computations were a little bit more involved because it's 3 by 3, that resembles what would happen for the 2 by 2. All right, where it gets a little different, and again, it's not too different, but different enough, is when you look at the eigenspace for a repeated eigenvalue. And so the repeated eigenvalue is lambda equal 3. You want to find u such that AU is equal to 3u. And so that is a minus 3 lambda 3 u equal to 0. All right, so I'm going to subtract 3 from the diagonal of A. If I do that, I get -2, 2, -2, -2, 2, -2, -6, 6, -6. Okay, that's if I take my original matrix A, subtract 3 from the diagonal, that's what I get. Okay, well, so now notice what's going to happen. This one's actually easier. I'm not even going to worry about multiplying through by the -2's. I'm going to subtract R2 minus R1, put that into R2, and I'm going to multiply R1 by 3 and subtract that from R3 and put that into R3. And might as well, I'm going to multiply R1 by 1/2 and put that into R1 after I've done that. If you do that, you get -1, 1, -1, But if I subtract row 2 minus row 1, I get 0, 0, 0. And if I do that operation here, I get 0, 0, 0 again. So I get 2 rows of zeros, not just one. Okay, so that's the big difference here. And so notice in so doing, I only have one pivot. I just have the one pivot. And so both of these guys, both are free. Okay, so you have 2 free variables, and that happens to correspond to the fact that that particular eigenvalue repeated twice. It occurred twice. All right, so let's let x3 be s, and let's let x2 be t. Okay, then let's go back to our equation. Okay, plugging those in, I have plus t minus s equal to 0. I'm just going to take that over. So x1 is t minus s. Okay, and so the eigenvectors this time, the u's, which are the vectors x1, x2, x3, well, I put a t minus s in for x1, a t in for x2, and an s in for x3. I'm going to pull the t's and the s's off each other. So I have t, t, s, 0, pardon me, plus negative s, 0, s, just grouping the t's and the s's separately. Off the first one, I'm going to yank out a t. And off of the second, I'm going to pull out an s. Okay, and remember, t and s are just real numbers, independent of each other. Okay. And so notice what the structure is here. All of the eigenvectors corresponding to lambda equal to 3 are linear combinations of these 2 vectors this time, not just one, they're 2 vectors. And so by definition, the eigenspace corresponding to lambda equal 3, that repeated eigenvector, is a span of 2 vectors, namely 1, 1, 0 and negative 1, 0. Okay. And so the basis for the eigenspace, or a basis for the eigenspace, is the set containing those 2 vectors. Okay, and so notice the dimension of this eigenspace is 2. Okay, that's different. The other ones had dimension of 1. They only consisted of scalar multiples of a single vector. This time, the eigenvector or the eigenvalue repeated, and so the dimension of the eigenspace increased. All right, so that was the keynote there. Okay, so that is all of the examples I wanted to talk about. It's a little longer of a lecture because it's kind of involved. So try to digest this notion of eigenvalue and eigenspace over the next few hours and whatnot. Do the homework problems, and then come back to me with any questions. All right, take it easy, everybody.